In this video, we'll discuss the property of weak duality in linear programming. So here we have the primal and dual LP written for the general case. So we have a maximization LP in the canonical form, and then we have its dual, which is a minimization LP in the canonical form. And to derive the property of weak duality, we will essentially go over the same exercise we went through when we did the motivational example, but now we are going to do it for the general case. Alright, so we have Z, the primal objective, and the primal objective is given by the summation of Cj's xj's for j between 1 and n. Okay. Then, essentially, to derive the upper bound on Z, what we did, we developed the dual LP in which the constraints were responsible for dominating the coefficients in the objective of the primal in order to obtain the upper bound that we want. Okay, so we look at the constraints of the dual, and we see that this is exactly what we have here. So the left-hand side of the dual LP is designed to dominate the coefficient in the objective of the primal so that we get that upper bound that we want, right? Now, the other way of looking at it is Cj is less than or equal to the left-hand side here, and this is what we're going to use here. So we'll replace Cj with something which is at least as large, and this will give us the less than or equal to inequality. So I write the summation sign as before, but now instead of Cj, I'm going to write the left-hand side of this constraint here, which is greater than or equal to Cj. So this will be the summation of aij's yi's for I between 1 and m. So we replaced C with the left-hand side of this constraint, and then xj will be there as before. Okay, so essentially this inequality that we just wrote, it came from the dual. So let me denote this inequality as dc, let's say, for dual constraint. So this was based on dc. Okay. Alright, so now we have this double sum here, and the terms are arranged in the way that every time I go over j's, I have the product of xj over the summation of aij's yi's taken over all i's, right? So this is the sum, and I can rearrange the terms as I wish. The result of summation is not going to change anyway. So I can say that this is the same as sum over I between 1 and m, and then the internal sum will be the summation over j's between 1 and n, aij's xj's, and then multiplied by yi's. It's actually the same sum as before, we just wrote it differently, right? So here the internal sum was over aij's yi's, and then we multiply the result by xj, and here the internal sum is the summation over all j's of aij's xj's, and then we multiply by yi and sum over all i's. But as a result, we will obtain the sum of all aij's xj's yi's both here and here. So it's the same sum, all right? We just rearranged it in a way to see what the coefficient is for each yi instead of expressing the coefficient for xj's here. And now recall that in our motivational example, to get the actual upper bound on the optimal objective value for the primal problem, we used the right-hand sides of the primal constraints. Okay, so and now when we rearrange the terms this way, we can see that we have this expression right here, which is exactly the same as the left-hand side of our primal constraint. Therefore, this is less than or equal to bi, And this is what we're going to do next. We will replace this sum here with bi, and we'll write another less than or equal to inequality here. And this will be the summation over i's between 1 and m of bi's, yi's. Okay, so and to get this inequality, we took advantage of the primal constraint. So if I denote it by PC for primal constraints, then we'll have this inequality following from these constraints here. Okay, so now what we obtained in the right hand side of this long inequality is exactly the dual objective, which we denote by W. So this is equal to W. All right. And as a result, this is what we obtained. So this is exactly the weak duality result. So it tells us that the objective of the primal for any feasible solution of the primal is going to be less than or equal to the objective of the dual for any feasible solution of the dual problem. So this W is exactly what we derived also in our motivational example when we wanted to obtain an upper bound on the primal objective. So why do we call this weak duality? Because it allows a strict inequality. All right, so in general, Z can be less than W, but the inequality must hold for every feasible solution of the primal and every feasible solution of the dual. And recall that the primal problem is a maximization problem and the dual problem is a minimization problem. If we switch these two problems their places, and we know that the dual of the dual is primal, so if we treated this problem as the primal, then of course you would have the opposite inequality, right? So you would have the objective of the primal then would be greater than or equal to the objective of the dual. So here you have max and here you have min. So then you have this relation. So the highest you can go with Z cannot exceed the lowest you can go with W. All right, so this is the weak duality property. So here it is once again written in the compact form. So we had the Z, we wrote the objective for the primal problem first, then we used this inequality right here to obtain the first inequality in this expression, then we just rearranged the terms in the sum to obtain this expression right here, and then we used the primal constraint to obtain the second inequality. Okay. And this way we obtain the weak duality property. So we'll come back to this point when we discuss the complementary slackness, which is one of the next topics. But for now, let's see what are the implications of weak duality that we can use in order to obtain the optimal solution to either primal or dual. So because this weak duality inequality holds for any feasible x for the primal problem, and for any feasible y for the dual problem, if I find a feasible solution x star for the primal and a feasible solution y star for the dual such that the two objectives match, so z at x star is the same as w at y star, then we can actually claim optimality of x star for the primal and y star for the dual. Right? So because, look, if let's say I fix one of them, so for example, I take particular values for y star and plug them in this inequality, then once the values of y star are fixed, this becomes a constant, right? And we have the inequality that for any feasible x, the objective z is less than or equal to that constant. So then if I find x equal to x star, where z actually matches that upper bound, then I can conclude the optimality of that x star, because whenever you reach the highest possible value, this is what optimality is about, right? So, and the same way going in the opposite direction. So if let's say I fixed x star first, and then I found y star such that w matches that lower bound that we obtained using x star, then we could claim the optimality of y star. So, and whenever we have the primal and dual objectives match, when they're equal, this is what we refer to as the strong duality. And in the next video, we will show that whenever the LP is of the optimal type, then the strong duality always holds, meaning that I can always find a dual optimal solution such that the objective of that solution matches the objective of the primal optimal solution.